Hello everyone, welcome to my channel. I am Sachin Kulkarni and today we'll have a session on StatPro, a small introductory session on how to model a cantilever beam and subject it with respect to the concentrated force at the free end of the cantilever beam. This will help us to understand what will be the bending moment diagram, shear force diagram and the magnitude of deflection that will play a key role in this particular analysis. So this is a particular StatPro icon that you've been resembling once you open and click it on the icon. So to begin with the project, we shall start with a new project, and you also have an option for the open project if it's already been created. Means already an existing project if we have, you can go to the open project and open the folder where that particular file is being saved. So since we are going to start with a new project, we shall click on the new project. As soon as you click on the new project, you will be getting the file name which you want to name it. So if you want to name it as the first session as practice 1, you can name it as P1. And then this will be the folder where you can save it, or else you can rename this particular folder. It will ask for whether you need to create that particular folder or not. So as of now, I shall continue with this particular G drive. Whatever the drive you want to save, whether it will be C, D, or the drive that is existing in your system. You can save in that particular drive and name a particular folder. It is always advisable to create a folder and save the stat file. Reason behind that is, once you create this particular stat file, it will be associated with n number of supporting files. So that will occupy a lot amount of space in your drive. For that reason, it's always advisable to create a folder and then keep on saving all the files that you have modeled and created in STAT. So these are the basic system of units that have been available here. And since we are following meter as the standard unit for measurement along the length, and the force unit will be kilonewton. If it is required, you can toggle and change that particular the system of units. So as of now, in this particular practice session, I shall continue with meter and kilonewton. So proceeding ahead, we shall move to next and then say finish. Once you click on this particular finish, you will be coming out to the graphical user interface screen of STAT, wherein you will be coming across the grid. We will not be working on the grid. I shall close this particular default system. So this is a particular screen wherein you will be having a StatPro and StatPro user interface screen, wherein we'll be learning how to model a particular beam, that is basically a cantilever beam, as this is an introductory session, and is subjected to respect to the point load at the free end. So once we start with this, we shall create a node. So basic operation is, first we need to create a node, then generate a beam, then assign the properties for the beam, support condition, and the loading type. These are the few steps that we are going to continue. So first one is the node, what we are going to create. So basically it will be adopting two types of coordinate system. One is polar coordinate system, other one is Cartesian coordinate system. If you are following X, Y, Z, it will be a Cartesian coordinate system. If you are following a circular type of orientation, basically for circular raft or water tank or circular structures if you want to model, then it will be a polar coordinate system, wherein you are going to assign the coordinates in terms of R, theta, and Z. So if you are assigning a rectangular square type of structure, it will be a Cartesian coordinate system, wherein we are assigning or the coordinate system in terms of X, Y, and Z. So this will be a coordinate system wherein X will be 0, Y will be 0, and Z will be 0, which means we will be creating that particular beam from the origin point. Then the second point, which is at a 4 meter distance, say the length of the beam or length of the cantilever beam is 4 meter, so X will be 4 meter, Y will be, Z will be 0. So these are the 2 points that have been created, and as mentioned earlier, the basic steps that are involved are to create nodes, generate beam, then assign the property for the beam, support condition, loading, and then perform the analysis. So we have created a nodes now. Next part is to assign the beam. To assign the beam, you can go to add beam here. So once you click on the add beam, you will getting an icon wherein it is plus then the beam. So you will be joining this particular 2 beams, wherein node number 1 and number 2 are being connected. This is beam number 1. node number 1 and node number 2 are connected. If you want to visualize this particular node numbers, you can go to right click, labels, then node number. Say OK. So these are the node numbers that have been visualized on the screen. Similarly, if you want to visualize the beam number also, you can go to labels, then say beam number. So this is beam number. Okay. So what it indicates is beam number 1 is connected between beam number 1 and beam number, node number 1 and node number 2. So this is how we are going to create the beam by assigning the coordinate and then the joining those particular coordinates to create a beam. Now, as mentioned, next procedure is to assign this particular member property. To assign the member property, go to commands, member property, prismatic. Commands, member property, prismatic. Prismatic means we'll be getting a sections here. The various types of sections and the geometry that you have in the library are circular, rectangle, T, trapezoidal, taper tube. So as of now, we shall take a rectangular type of section. The depth of the beam we can consider as 0.3 and the width as 0.23. The material type what you can select, we have various types of library material type in the library. That is steel, stainless steel and concrete also. So we shall follow concrete part here, then say add, close this part. Now the question comes is how to assign this. So to assign this, click on this particular member, it will turn to blue, and then click on this part. Click on this particular beam, so it means it has been assigned to selected beam. Again, I shall repeat, as it is, when you click on here, it will be turned to blue. Default system here is use cursor to assign. This is a cursor which you are going to assign here. So automatically from use cursor to assign, it will be shifted that particular toggle to assign to selected beams. Then say assign. So the beam number 1 is assigned here. That is R1 means, R means reference number. Reference number 1 is assigned with a depth of 0.3 by 0.23. If you want to see this particular part, you can double click this and you can see the property here. So this is 0.3 by 0.23 as the width. And if you want to see the 3D view of this, you can see the 3D view of this. Then, as mentioned earlier, we need to create a node. The creation of the node here. We need to join the nodes. That's the creation of the member. Then we need to assign this particular member property. To assign the member property, you need to go to commands, member property. The next part is to assign the support condition. Because in finite element analysis, it is nothing but the boundary condition that will play an important role in asserting the results of what we want. Because the boundary condition will help you to understand what type of BMD it will be, what type of SFD. It will not be the same for simply supported and neither for fixed. Depending upon the boundary condition, basically what we call it as a support condition, the end condition or the results will change. So since it is a cantilever beam means one end is fixed, the other end is free. So we shall go to fixed end here, support, fixed end. Then say add. The procedure remains the same here that we have assigned for member property. Now S1 is no support, S2 is support 2. Support 2 means fixed. So you are going to assign this particular part to a node here. For that you need to select a node cursor. Then select this particular part, assign to selected node, assign. So you have created a beam, then assign the member property, then assign the support. The next part is to assign the load now. For that again you need to go to commands, loading, primary load. Primary load we shall say it as point load. So point load, then say add, close. To this particular point load you need to assign where exactly it should be. That means whether it is on the member. When it has been placed on the member, we call it as member load. If it has been placed at the free end of that particular beam, we call it as the nodal force. So this we come across on the field when we are constructing a brick wall. So generally the brick wall has been constructed on the beam. So in that particular case, we call it as the member load. If you happen to place any point force at the free end of the beam, we call it as a nodal forces at the free end of the beam. So this we are going to assign it as a nodal force here, point load, add. So nodal load here. If you happen to see the UCS icon, this is Y is vertical, X is horizontal, Z is along the width. So I am going to assign the force along the vertical direction minus 10 kilonewton. Say add, close. So this will be assigned to this particular node now. So one end is fixed, the other end is free. So I'll be assigning to the free end here. So you need to assign for selected node. Again, I shall repeat the procedure. Go to node cursor. Once you move on the screen, it will come with an arrow and then a dot, which is nothing but a node. Then select this particular node where you want to assign this particular nodal force. Then assign to selected node. Assign to selected node. So this will be a force now. Now if you see, that is quite huge number because it has been scaled up now. So you can reduce this particular scale. Go to labels, scale, apply immediately. That is the point force here. You can see that particular line, which was quite a huge one, is been reduced to this lower scale, to the scale what we have to the screen size. And if you want to see that particular nodal force, go to label, load value. Okay. So this is minus 10 kilonewton applied along the vertical direction. And it is minus for the reason it should be in the downward direction. Y is upward is positive. So this completes the whole process of creating the member, assigning the property, then assigning the load. Now the most important part is to give the command. You need to assist this particular software to perform the analysis. For that, go to commands, analysis, perform analysis. Then say OK. So this will help for the particular software to conduct this particular analysis procedure. So go to analyze, run analysis. Then say save. So this particular process is completed with 0 errors and 0 warning. To view the results, you need to go to post-processing mode. In either of the option, either in view output file, and if you stay in stay modeling mode will help you to only to understand how to create that particular model. It will not show you any results here. So for that reason, you need to go to post-processing mode. So basically, we have 3 phases: modeling, processing, and post-processing mode. So we need to go to post-processing mode. So then, done. Apply. Okay. So this will, by default, it will show you the deflection. This green line, what it will be indicated is the deflection value. So if you want to view the results here, go to results, view value, beam results, then displacement maximum annotate. So this will show you that there is the displacement value, which is 19.054 mm. So which is nothing but basically it is WLQ by 3I. L is 4 meter, W is 3, E is the value that you are going to assign, and I is the moment of inertia. So this is a rectangular section, so I will be equals to BDQ by 12. So once you are done with this, so you can see this particular bending moment diagram also. Since it is a point load, it will vary linearly. So this will be linear bending moment diagram. As the span is 4 meter, point force is 10. So bending moment value, it will be maximum at the support, and the perpendicular distance for the point force will be 4 meter. So 10 into 4 will be 40. 40 kilonewton meter should be the value that you should visualize on this scale. So for that, go to beam results, bending maximum, annotate it. See, 10 into 4 will be 40 kilonewton. Likewise, if you want to visualize the shear force value, which will be Fy. For bending moment, it will be Mz. Shear force, it will be Fy. So what is shear force? It is a net reaction force that will be available at the support. So net reaction force, you have only one force, 10 kilonewton downward. So shear force, it will be in the net reaction will be 10 kilonewton here. So which will be shear force diagram, which will be upward. And the value, if you happen to see, results, view value, beam results, shear force maximum, annotate. See, 10 kilonewton is the shear force value. So this is how we are supposed to visualize the bending moment value, shear force value, and the deflection value for a simple cantilever beam subjected to the point load at the free end. Okay. So in the next upcoming classes, we shall continue with some of the other lectures on StatPro and also with respect to the validation of this particular results by considering this particular process and what will be the deflection value based upon the primitive equations what we have. Thank you everyone. Have a nice day.